Okay. So, welcome to the second lecture on hydrostatics and stability. In the last class, we discussed about the block coefficient and we left off at the block coefficient. Now, there are a couple of other coefficients which are also important, though the main one is a block coefficient. One of them is the Midship coefficient. It is known as a Midship coefficient. Um, it is defined as the ratio of the sectional area underwater to the breadth and draft, which means it is defined to be Cm. Midship section area is defined as Cm is equal to Am by B into T, where Am, as I told you before, we divide the ship on in two ways. Um, if you if you define this to be the ship, this direction is known as the longitudinal direction, and when you see from here, what you see is that area you see is this, it will look like this. This area is known as the sectional area. The direction is known as transverse direction, and it is known as the sectional area. Now, this area is what we are talking about here. So, it is this area divided by B, which is this is B into draft, this draft. So, the midship sectional area will look like something like this. This area, sectional area, which is written here as Am divided by B into T. So, you will have the sectional area at the midship section. It is known as the midship coefficient and designated as Cm. So, this is the second coefficient. Then third, we have some more coefficients. The first, of course, I already told you, is the block coefficient. Block coefficient, and then you have the midship sectional area coefficient. Then we call something as the prismatic coefficient. Prismatic coefficient is defined as Cp is the ratio of the molded displacement volume del now. It is a little more difficult to draw this figure, so I leave it. Prismatic coefficient is defined as the ratio of the displacement of the ship. Del is the volume displacement of the ship. You know that del is always the volume displacement, and delta we call it as rho into del. It is known as the displacement weight of the ship. So, you have Cp, the prismatic coefficient, as delta del divided by Am into L, where Am is the midship coefficient. So, it is something like this. If you think this is the length of the ship, if you consider this to be the length of the ship, then this area, midship sectional area into L, will give you, this is the length of the ship, this is the length L of the ship. Midship sectional area into L is this, and it is the denominator, the numerator is taken up by del operator. So, this is the prismatic coefficient, and then there is a water plane area coefficient. This is known as a water plane area coefficient, is another coefficient. It is denoted as CWL is equal to AW divided by L into B. That is, if you have a shape like this, AW is the water plane area. Let us say that this is the water line, then this is the water line, this is the ship, this is the water line, and then AW is the area, this area is this area, water is this water plane area divided by L into B. L is this distance L and B is this breadth B. This is known as the water plane area. So, then there is a vertical prismatic coefficient, defined as CVP is equal to del divided by AW into T. So, I leave it at that. The definition itself says what it is. CVP is equal to del divided by AW into T. T is the draft, AW is the water plane area. You should know what is the water plane area for sure. Water plane area means that if you have the ship like this, there is a water line, the area that is completely at the water line there is an area for the ship, horizontal area of the ship, that area is known as the water plane area, and that is what is coming here as AW, AW into T is the draft. So, we defined a couple of things in this chapter. We defined a block coefficient, we defined what is known as the displacement, displacement volume, displacement mass or weight, then midship coefficient, midship coefficient, then midship sectional area. Before doing midship coefficient, we learned what is the midship sectional area, then prismatic coefficient, then vertical prismatic coefficient, water plane area. You among these I think what is water plane area is very important. You have to know what is the water plane area. Then of course, the water plane area coefficient. These are some of the terms that we learned in this chapter. Then so this Cp, you will see that when you do it, it becomes Cb by Cm. The prismatic coefficient is equal to the block coefficient divided by the midship sectional area coefficient. So, this is where we leave chapter 1, and next is the second part, which deals with Archimedes principle. This is the first principle of this topic, the most basic principle with which all the rest of the study proceeds. As you know the famous story, Archimedes is supposed to have discovered this, and when he discovered it, he was so excited that he ran naked on the streets shouting Eureka. That is a famous story. That is the Archimedes principle. So, let us take a look at what is the Archimedes principle. Before we do it, we make some assumptions. Water is incompressible. Incompressible is a word used in fluid mechanics, which implies that there are not any density changes in the medium. So, the water has a constant density, it does not have any variabilities in density. So, that is water is incompressible. Then water is an ideal fluid. What we study here is that it is an ideal fluid. It is again an important term in fluid mechanics. You have two types of fluids, ideal fluids and viscous fluids. Now, all the liquids that we consider, including water, mainly water, are all viscous fluids, but in many cases we can assume that the fluid is ideal without any viscosity, and that assumption is made in this case. Then we say that there is no surface tension. There is no surface tension, that is an assumption made here, because that will make changes to the it will make change, it makes the makes changes to the water line. It will not be a straight line as we are assuming here. That is the last assumption, that is the water surface is plane. So, the surface of the water is plane. So, these are some assumptions we make, and then we go into what is known as the Archimedes principle. The principle itself states that when a body is immersed in water, in a liquid, if a body is immersed in a liquid, it will experience an upward force, and the magnitude of that force is equal to the weight of the liquid displaced. So, when the body is immersed, it displaces some liquid. The volume of the liquid displaced will be equal to the volume of the solid immersed. The part of the body immersed has a particular volume. That volume will be equal to the volume of um, the volume of the liquid displaced, and in addition, if rho is the density of that medium, rho into that volume will give you the weight of the liquid displaced, and that is the amount of weight that is displaced. That is what this figure tells. Any object wholly or partly immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. So, weight of the fluid displaced by the object, here you have seen this weight is put into the water and it has displaced the 3 pounds of water. So, it says here 3 pounds of water. So, this is experiencing an upward force of 3 pounds of water. This upward force, this force is known as the buoyancy force. This force is known as the buoyancy force, and this buoyancy force is equal to the weight of the liquid displaced, as this figure clearly states. Okay. Now, there are many derivations for the Archimedes principle. We will take we will take a look at some of them. Now, let us suppose that there is a solid which looks like this. And let us suppose that, so this is a solid and these are its faces. One is this face, 2 is the face below, it is not this one, it is the face below, then this is 3, this is 4, that is 5, this is 6. So, these are the 6 faces of this solid, and let us assume that the water plane is here. So, this is the water plane, it hits, it's touching the surface 6 and surface 3 at this point. So, the body lies like this. Now, let us find, you know that as per the physics, all these phases will experience a force. They will experience a pressure due to the liquid, but they will also experience a force. Now, for example, the fourth side, this is the fourth side, this one, the curve, I mean the phase opposite to 6, the phase opposite to 6 is 4. So, F4 will be equal to now if you are familiar with little bit with the hydrostatics, it will look little bit familiar with the hydrostatics of fluids. So, you will see that if this is the body, this is the body, we are looking at this is the phase 1, here you have the phase 1, and if this is T, and then you will have the pressure distribution. Pressure distribution is given by rho g z. This is the pressure at any depth, it is given by rho g z, where z is the distance from the free surface. Now, this rho g in this book, rho g is always written as gamma. So, we have rho g is gamma. So, gamma z will give you the pressure at any point. Now, pressure into the pressure gamma z into dz will give you the force per unit length of the side. So, if you multiply it with L, you will give the force, you will get the force on the side 4. So, actually the pressure distribution will look like this. it will look like a triangle because it is rho g z. As z increases, the value keeps increasing. So, it will look like the whole area will, the whole picture will look like a triangle between pressure and depth. So, L into, and of course, this comes because P0 L into T. P0 is the atmospheric pressure into L into T will be experienced by the side 4. It is experienced on the whole area, the atmospheric pressure is there plus the pressure due to the liquid. This is the atmospheric, this is due to the atmospheric pressure and this is due to the liquid. So, F4 is known and then you need to find out F6. F6 will be, if you see, F6 will be given by exactly opposite Now, you know that we do pressure into area, PdA will give you dF. So, dA, the direction of dA defines the direction of the force, pressure has no direction. So, force has this direction. So, in this case since the area vectors diverge in the opposite directions, one goes like this, one goes like this, it will be of a different sign from the previous one on F6, that is minus L gamma z dz plus minus P0 LT, both will be negative. So, when you add these two together implies F4 plus F6 is equal to 0, both of them are opposite of each other. So, when you do F4 plus F6 you get 0, which shows that when a body is just simply put into the water, it does not experience any horizontal forces. This is known because otherwise it would be a kind of free propulsion without any, without applying any power you get free propulsion, it does not happen. So, this is known, but we just show it clearly. Now, the pressure, but now let us look at the vertical direction. This one F1, as you can see, this is the one phase, this is the one phase, on that F1 will be equal to minus P0 into L into B. L is this and B is this. So, L into B gives the area, P0 L into B gives you the force on the side 1, force on the side 2 which is at the bottom will be minus P0 into LB, I mean plus P0 into LB. If this dA you take it as negative, then this dA you have to take it as positive. So, plus P0 LB plus gamma into LBT. LBT is the volume underwater, this is T. Gamma into T will give you the pressure at that depth. Okay, it is gamma z, it is just gamma z. So, gamma into T gives you the pressure at the depth of 2, at this depth of 2 what is the pressure is given by this gamma into L, gamma into T, and then into L into B will give is the multiplication with area, therefore, you get the total force. So, here F1 plus F2 is therefore equal to gamma into LBT. LBT is the underwater volume and multiplied it with gamma, which is the density of water, it gives you the underwater weight. Underwater weight, which what it really means is that it is the weight of the liquid displaced. This is the weight of the liquid displaced. So, you get that F1 plus F2, the net force on the body, the which is a net upward force, this is upward, it is directed in the upward direction pushing the body up, as you can see it given here. It is given by 3 pounds, as you see here, which is the 3 pound weight of the water, is it is directed upwards, it lifts the body up, and this is the weight of the liquid displaced is equal to the force of the body. This is the Archimedes principle. It can be done in some other ways as well in the same figure. If, for instance, um, the area under a pressure the area under a pressure area or a pressure length curve will give, you know, that the area under a pressure length curve would give you the force on a body. So, if you take that half base into altitude, the area under the curve, under this curve, this is the pressure length pressure, one side is pressure. If you consider one side as pressure and one side as the bed, one side as the length, if it's if you put it on a pressure length curve, then the area under the curve will be half base is equal to gamma t. The pressure at the base is gamma t, half base into altitude is t. So, you will get half gamma t square. This will be the area of the triangle, and the force on the force on 4 will then be equal to L into half gamma t square plus P0 LT. P0 LT comes from the atmospheric pressure, and similarly it is the same as what we got before. So, this is another way in which you can do it. If you do not like integrals, you can just take it as the area under the curve and do it that way as well. Okay. Then we can look at the general case. Let us assume we have a coordinate system like this. Y, Z, X, suppose you have a body that is immersed in the liquid. Let us suppose that the top, let us suppose that this is something like the center, and let us suppose that the surface is given by Z equals S1 F1 of x comma y. The bottom is given by Z equals F2 of x comma y. So, the surface is defined in this fashion. The top half of the surface, top part of the surface is defined as Z equals, the upper part of the surface is defined as Z equals F1 of x and y, and the bottom half is defined by Z equals F2 of x into y. Therefore, Z equals F1 of x into y is the top surface S1 in S1. In S2, Z equals F2 of xy is the basic definition of the surface. And if you take this, and in this we can see that the pressure force is given by on the surface A. Let us take on the upper surface, the pressure force on the upper surface is equal to P dA equals gamma z, pressure is gamma z, gamma F1 of xy will give you the surface gamma, and dA. Now, the vertical component of the force, this force, if you look at this figure, we have now considered a small element d like this. This will be directed in a direction normal to the surface, it is dA, it is directed normal to the surface dA. It will have an angle with the vertical, it will have an angle with this vertical, it will whatever be that angle, that normal, let us suppose that angle. So, gamma F1 of the vertical component of the force is the vertical component of this pressure force, is given by gamma F1 of xy into dx dy into cos of I mean it will be dA into cos of the angle between n and z. So, cos of the angle between n and z will give you, so this will give you the vertical component of the force. All I have done here is if n is the normal like this, then the vertical component of the force, that is the component of this force in this direction, is this force into cos of the angle between them. That will give you the component of the force in the vertical direction, and that is what is given here. Vertical component of the force is equal to gamma 1 into dA into cos. Now, dA into cos nz, here if you put it, it will be an element dy dx. This is basically the projection of dA cos n z is actually the projection of dA on to this plane, and that is given by gamma 1 f of this becomes dx dy. And similarly, by exactly the same reasoning, we will get the from the bottom side, the vertical component of the force, the vertical component on side S2 will be gamma 1 F2, this is F1, F2 of xy into dx dy. Therefore, you get the total force F is equal to the sum of these two, gamma 1 into F double integral, or rather I will write it in that way, df is equal to gamma 1 into f1 of xy dx dy, and the top surface, if that direction is taken as positive, the bottom surface the direction has to be taken as negative, minus f2 of xy dx dy. So, df that is equal to gamma 1 into integral f is equal to over the surface area f1 of xy dx, f1 of xy minus f2 of xy dx dy. Now, what is this? This is basically f1, this is basically z dx dy. It is equal to the volume of the body. This is the volume of the body submerged, the submerged volume. So, gamma 1 into submerged volume, and therefore, what we get here is that the force on the body, the upward force or the vertical force, is equal to gamma into z, gamma into whatever is gamma into integral of gamma into volume under volume submerged, gamma into volume submerged, that double integral over s, and that was giving you the volume. So, it is equal to the volume submerged. This gives you the upward force on the body, and similarly, if you try to look at the horizontal component, you will get it will be like this. You will have to on this figure, you will have to get the horizontal force, you will have to take the if dA, you will have to take the projection onto this side, yz side. So, that will give you p cos p into cos of the angle between n and z will n and x will give you gamma into z dy dz. This will give you this is the horizontal force on one side, the other side the horizontal force will be minus gamma z dy dz, which will imply that the two forces when you add together will sum up to 0, and therefore, the body does not experience any horizontal movement, does not experience any horizontal force due to just being submerged in the liquid. So, that we know. So, there is no horizontal force, but the vertical force is given by is equal to the weight of the liquid displaced. The vertical force is equal to the weight of the liquid displaced. Now, for a body that is freely submerged in water and which is for a body that floats on water, means it is at equilibrium, it remains at equilibrium, it is such that it is at in a stable state it is without any support, it remains floating on the surface of water, you can give this formula delta, which is equal to the weight of liquid displaced is given by gamma into del, where del is the underwater volume. So, if you have a body like this, if this is del, it is very important to note here that we are talking about the underwater volume. We are not talking about the total volume of the ship. This is the total volume of the ship. We are talking about the underwater volume of the ship is del into gamma. Gamma is the density of water and not the density of the material of the ship or anything. These are two confusions that come up very many places, that is gamma is it either the density, this is actually the weight of the liquid displaced. Volume of liquid displaced is equal to the volume submerged, because what is gone in has to go out, because there is no other way. If x amount of or v amount of volume goes into the water, then v amount of liquid will be displaced, that is del, and when it is multiplied by the density of water, density of the liquid displaced, it is the weight of the liquid displaced, you will get the weight of the liquid displaced. And if the body is floating freely, then this gamma into del is equal to W, that is the weight of the body itself. If the density of the material of the body is rho, so it is rho into V, the total volume of the body. So, rho is the density of the material, means rho into total volume of the body will give you the rho into total volume of the body will give you the weight of the body, down. So, in this figure, if we had some case like that, we could say that the weight of the body, if in this case there is a tension acting upwards, there is a weight acting downwards, and there is a 3 pound force acting downwards. In this case, I would say that T, the tension, plus 3 is equal to W, the weight of the body. So, T is the tension in the rope, plus 3, which is the upward force, is equal to W, the weight of the body in this case. So, in any case, in all other cases you will have delta equal to the weight of the liquid displaced. Then we can write this in many ways. For example, gamma into Cb into Lbt. Cb is the block coefficient. So, Cb into Lbt, I have already told you Cb is equal to Lb, it is equal to del divided by Lbt. So, Cb into Lbt is equal to del. So, gamma into del is given by gamma into Cbt. This is equal to the total weight on the ship. This is equal to the sum of all the weights on to n Wi. It is equal to the sum of all the weights in the ship Wi, where Wi is the weight of the ith item of the ship, and there are different items on the ship that is given here. Then so, this is something about the forces. Then in addition, in this subject we will deal with two things. We will deal with forces and we will deal with moments. Moments, as you know, occur in the ship itself. For example, suppose that a body is floating like this, and the weight of the body acts down here at G. At the center of gravity of the body, a weight acts down, and at the center of buoyancy, a force acts upward. Now, the center of buoyancy is defined as the centroid of the underwater volume. So, you know that if a body is floating in water, a part of it will be underwater. Centroid of that underwater part is known as the center of buoyancy. So, it is the centroid of the volume, not centroid of the weight, it is actually a centroid of the volume of the underwater volume of the ship. So, this is known as Cb, this is known as B, we call it as B always the center of buoyancy, and G is the center of gravity of the ship. Now, the center of gravity of a ship depends upon the weights on the body. It does not have anything to do with the water or the upward force from water. It has to do with the just the weights that are placed on the body. So, when you place weights at different places, you get the center of gravity. So, you have in this case, for instance, you see center of gravity and center of buoyancy is in the same straight line. Center of gravity and center of buoyancy are in the same straight line. Then so if they are in the same straight line, you can see that they do not produce any moment, they do not produce any moment. So, this system does not feel any moment, but let us say that I removed some weight from here and pushed it here. So, some of the weights on the ship on this body, whatever this is, some of the weight is taken from here and put on this side. So, there is a shift in the center of gravity. So, you will have the system like this now. Center of gravity is here and the center of buoyancy has not changed, center of buoyancy is still at the same place. So, at this point a weight delta acts, at this point the weight W acts. So, at that point the weight W acts downwards and at this point delta acts upwards. So, so we have the center of gravity and center of buoyancy at different points and they are not on the same straight line. So, this and this is in this line, it acts here and this acts in this line. So, we have two forces that are acting in opposite directions and separated from each other. So, as you know, they will produce a moment. If there is a in this case there is a tendency to trim like this, like this. So, it has a tendency to heel, the word is not trim, sorry, it is heel, it has a tendency to heel like this, and then the body will become like this. Body will become like this. In this case G B, what will happen is that the body will tilt such that G and B again comes in a same straight line. The moment it comes in a same straight line, the moment stops and the body is stable. So, in this case the body remains like this in this inclined position. So, this is what we mean by having by studying by meaning about the movement, about the moments. Then comes a very important concept, that is this is many cases not studied properly. This should be looked at, that is about the water plane of the ship. Now, there are, now let us suppose that this is the initial water plane of the ship W0 L0, and let us suppose that the body tilts like this. Now, this figure is very important that you understand this figure properly. What has happened here is really that this body it is like this. So, this body, it was initially horizontal, it was in a very horizontal state, and then that body tilted like this, tilted in this direction, the body tilted in this direction, and therefore, some part of the body has gone in at this side, some part of the body, another part of the body has come out at this side, and this is still the water line. So, instead of trying to draw the figure of the, instead of trying to draw the ship initially at like this and then it has tilted like this, instead of drawing the ship like that, it is easier to make the water line, it is instead easier to tilt the water line. So, if initially the water line is like this, if the body has tilted in this fashion, if something has gone under here and come out here, if you draw the water line in this fashion, this is what it is. So, what this figure shows is really that the body which was initially at W0 L0 when it was in a horizontal position tilted in this direction to become W phi L phi like this, W phi L phi like this, and that tilting, instead of looking as if the body is tilting, we write the water line as tilting. So, this is done, this is called as W phi L phi, this is the new water line, and this figure indicates that this body is not now in a is not in a straight position, but it is in an inclined state. There are some other formulas for that need to be satisfied in case of floating bodies, that is for the body to float upright. So, it is just not enough that the body floats, just floats, it is also important that the body or the ship, not a body, in case of a ship it is important that the ship floats upright, that it does not heel or trim too much, it floats upright. So, so there are some other formulas that need to be satisfied, that is what we are going to do now, next. So, initially we have G here, this is known as G0, and then you have at this point B0, G0 and B0, and here you have W, the weight of the ship acting, here you have delta, the ship, the weight acting upward, the buoyancy force acting upwards, then the body tilted and B0 shifted to this point B phi, it is the new point, and the vertical at that point is given by this line, somewhere here it hits the vertical, let us say that G0 is here, okay, and B1 B phi goes up and hits the vertical here. This point of intersection is known as M. Since the figure is a little confusing, I did not draw it properly, let me do it again. This is the body, okay, and initial water line is here W0 L0, and here you had G0 and here you had B0, then something shifted and as a result the body had to tilt, this is known as this much is the new water line W phi L phi, and it has shifted here B phi, because of this some wedge has gone out here and some wedge has come in here, therefore, the B will move in the direction of increased volume. So, B0 to B phi, and here if you draw a vertical, so this is the initial vertical. So, if you draw a vertical here, this hits the original vertical. Remember, this line is vertical because this water line is always vertical, W phi L phi is a horizontal line, not vertical, W phi L phi is a horizontal line. So, perpendicular to that it is always the vertical, this is a vertical line. So, B phi into M is a line, and this M is known as the Metacenter, a very important concept in naval architecture, it is known as Metacenter, Metacenter point M. Then there are a couple of okay, before I go into that, we should, this is how it will look. For instance, in the in this case, the ship has tilted in this direction, some part has gone in here, some part, this is the initial W, in this case it is different, the initial WL is given like this, I mean the initial is WL1, it was when the ship was stationary, ship was horizontal, then when it tilted the water line became WL like this, B shifted from here to here, B initially you have B and this is B prime. So, there is a transfer of wedge to one side, this is the figure, then and when you look at different points, these are the different points that you need to know in this case. For example, M is a metacenter, it will be at the top mostly. G is the center of gravity coming below it here, then B is the center of buoyancy coming here, then K is the keel. Keel, you know, is the bottommost part of the ship, it is the bottommost hull part of the ship is known as a keel, K keel, and K is the basic reference line, reference point from which all other points are considered measured. So, K is defined to be z equal to 0 and all these have particular values. So, you have Kb, you have Kg and you have Km, Gm, Bm, different things we have, different things we call different thing differently. For example, there are two things, one is called Gm, this is known as metacentric height, it is Gm, and then Bm which is known as metacentric radius, it is known as Bm. So, Bm is known as the metacentric radius and Gm is known as the metacentric height. So, here you see everything Bm, you see that Bm is known as the metacentric, this is the metacentric radius, Gm is the metacentric height, and then you have Km, that is another parameter which comes, and a couple of just small points here. First of all, if suppose that initially the center of buoyancy waterline was a WL, let us suppose that WL was the initial waterline, B is the centroid of the underwater volume, I have already told you it is the centroid of the underwater volume. So, you have B. Now, suppose that due to some reason the waterline the ship sunk a little bit more such that the waterline has raised above and it has now gone to WL1. If that happens, then the center of buoyancy B1 as the waterline goes up. So, that is how the ship's center of buoyancy behaves. The next one is about G, it is given here. In case you add weights, G shifts towards that point. So, whichever point in which you add some weight, G shifts towards that point. If you remove weight from some place, then G moves away from that point. So, G moves away from weight removal, G moves towards weight addition and G moves in the same direction as the weight shift. So, if there is a shift of weight, body will move in that direction. Then so, in this figure we have seen that this is M above G and that is a condition possible. Now, another condition is also possible. Now, as you can see, when it reaches this condition, here you have a weight delta, weight W, and here you have this weight delta and the displacement delta and W. You can see that in this case there is a tendency for the body to shift back to its original position of equilibrium. Before we do that, we have to define what is equilibrium. There are in general we say that there are three types of equilibrium. We call it stable equilibrium, neutral equilibrium, and unstable equilibrium. Now, stable, the meaning of these terms are this: a body is said to be in stable equilibrium if suppose it is in some position and some force acted on it or a moment acted on it to change its position, its orientation something, and the moment the force is removed, the body returns back to its original position again. That kind of equilibrium is known as a stable equilibrium. Now, if on the other hand, if a body is in some position, suppose a force acts on it and it continues as long as and it tilts, and when the force is removed the body does not come back to its original position, but remains as such without changing its position in a tilted position or in some other form, mainly in the tilted form. It remains with an angle of heel. If that happens, then it is said to be in neutral equilibrium. And the third one, unstable equilibrium, is if the body is in a particular position and if a force acts on it or a moment acts on it, and if a moment acts on it and it tilts, then the body, if the body does not return to its original position, but it continues to continues in its original tilting, increases the tilting and finally such that it capsizes, such a situation is known as an unstable equilibrium. So, these are three forms of equilibrium: stable, neutral and unstable equilibrium. Unstable equilibrium is when the body capsizes, once the force is removed also it capsizes. Stable equilibrium, the body returns to its original position after the application, after the removal of the force or moment, and neutral, it remains at the same position. So, these are some forms of equilibrium. Now, we need to figure out how this applies to the case of ships. I mean how the stability parameterization, that is the next step, that we will continue in the next lecture. So, today we will stop here. Thank you.